In this video, we're going to go through the easy questions on momentum and conservation of momentum. Question 1a, write an equation for the momentum of an object in words. That is going to be momentum is equal to mass times velocity. Part II, state the SI units of momentum. So that is kilograms meters per second. So we can work that out from this equation because mass is in kilograms and velocity is in meters per second, and we're timesing them together. Question 1b, a railway carriage of mass 1,100 kilograms is rolling on a track at a speed of 6 meters per second. It hits a stationary carriage. That is important. It's not moving. It's got no momentum. As shown in figure 1, carriage C2 has a mass of 3,300 kilograms. So first thing we've got to do is calculate the momentum of each carriage. So before, we're going to do mass times velocity for each. So for C1, its mass is 1,100, and we're going to times it by the speed that it is going. So the momentum is going to be 6,600 meters per second. Part II, the momentum of C2 is going to be 0 kilogram meters per second because it is stationary. So we'd do its mass times its velocity, but its velocity is 0, so its momentum is going to be 0 as well. Question 1c. At the moment of collision, they become joined and they move off with a velocity v. Use your answers from part B and the conservation of momentum to calculate the total momentum after they have become joined. So even though it's just 3 marks, you are just stating something really basic here. So if we do our momentum before, that is going to equal the 6,600 that we just worked out plus 0. So our total momentum before is this, and our total momentum after must equal the same as before because of the conservation of momentum. So it's 6,600 meters per second. One D is to calculate the total, the final velocity of the carriages joined together. So we know that our total momentum, which I'm just going to use a P for, is 6,600 kilogram meters per second, and that's equal to the mass times this unknown velocity. So we need to know what the total mass is, so we can work that out from the individual masses added together. So if we add 1,100 plus 3,300, those were the masses of C1 and C2, we get 4,400 kilograms. So to work out our final velocity, we're going to take our total momentum, divide it by our total mass, and we get 1.5 meters per second. So that is our final velocity of both of the carriages joined together. Question 2a, a stuntman of mass 85 kilograms is being trained to jump off high objects. He steps off a roof and falls vertically. Just before he hits the ground, he has this velocity, 9.08, and after he lands on the ground, he remains at rest. So we need to calculate his momentum just before he hits the ground. So his momentum is going to equal his mass times his velocity. This is part I. So we're going to take his mass of 85 times by his velocity, and we're going to get roughly 772 kilogram meters per second. Part II, after he has landed, so it says he remains at rest after he's landed, so his velocity after he's landed is 0. That means our momentum is also going to be 0 kilogram meters per second. Question 2b, using your answers to part A, calculate the change in momentum of the stuntman during landing. So that's our symbol for change in momentum. So we're going to do the momentum after, take away the momentum before. So that's going to be 0 minus 772. So our answer is going to be negative 772 kilogram meters per second. Question 2C, calculate the impulse. So impulse is a word that we don't need to use in WJEC. It just is another word for the change in momentum, basically. But we tend to use, if we're talking about impulse, we tend to use this other equation. Change in momentum divided by change in time equals 4. And that can be rearranged to give change in momentum is force times change in time. However, here it's just asking us for the impulse, which is exactly the same as change in momentum. So here our impulse is just going to equal our 772 kilogram meters per second, or we can use a different unit if we want for impulse, Newton seconds. Question 2D, the stuntman keeps his legs fully rigid and the time for the impact is 4.2 milliseconds, ms. Calculate the magnitude of the force. So we're going to use the equation that I put above there. Force is the change in momentum divided by the change in time. So we're going to do 772 divided by 4.2 times 10 to the power of -3, because it's milliseconds, not normal seconds. And if we type that into our calculator, you get an answer which rounds to 184,000 newtons. Newtons is our unit because we're working out force. Question 3A is talking about a bullet, so we might be talking about an explosion here. We've got a bullet leaving a rifle with a given momentum. So first of all, state the momentum of the rifle before it is fired and give a reason for your answer. So originally, the momentum is going to equal 0. So that would be our first mark. And that is because the rifle and the bullet are stationary or not moving. So before we fire it, there's no movement going on, so our overall momentum is going to equal 0. Question 3B, calculate the velocity of the bullet just after it is fired. So for our bullet, we've got a mass of 20, that's for our rifle, and the momentum of our bullet is 4. So if I just draw a picture for you to work that out, we've got our bullet going this way, its momentum is 4, and we've got our rifle going that way, which its momentum is also going to be 4, but in the opposite direction, so that it cancels out, and we end up with an overall momentum for the system of 0. But so we've got our momentum of our bullet, because it says in the question, is going to be 4 kilogram meters per second, and our mass of the bullet is equal to 20 grams. Don't forget that's in grams, we usually work in kilograms, so we're going to have to do some converting there. So momentum is mass times velocity, and we're working out the velocity here, so we're going to do our momentum divided by our mass. So we're going to do 4 divided by 0.02, so I've divided it by 1,000 to get it into kilograms, and if I work that out, we get our velocity of our bullet is 200 meters per second. Question 3C is talking about after the rifle has been fired, state the total momentum of the rifle and the bullet. So for the first part, we're going to say momentum before equals momentum after. And we know that overall it's going to be 0 kilogram meters per second because it was stationary before. So before we did anything, we had 0 momentum because nothing was moving. Therefore, we must have total momentum after also of 0. And part II, calculate the recoil momentum. So it's going to be 4 kilogram meters per second. So it's going to be the same as the bullet. The recoil momentum of the rifle is going to be the same as the bullet, but in the opposite direction. To the bullet. It's really important that we state that so that it still agrees with the conservation of momentum. So the rifle goes 4 kilogram meters per second one way and the bullet goes the other way. So overall, the system has not changed at all in momentum. It's still 0 kilogram meters per second. Question 3D. The bullet has a momentum of 3 kilogram meters per second and it takes 2.5 milliseconds to be stopped by the target, calculate the average force. So we're going to use this equation. Force is equal to the change in momentum divided by the change in time. Our change in momentum is 3, because it says it's 3 just before it hits the target, and our time is going to be 2.5 times 10 to the power of minus 3, because it's in milliseconds, and if we type that into our calculators, we get 1,200 newtons. Question 4a is about Zorbs. So we've got two Zorbs that collide head on with each other, and we've been given its mass and their speeds. So for part A, we've got to calculate the momentum of Zorb A before collision. So we've got the speed of 2 that I can spot there, and it has got a mass of 75. So it's 150 kilogram meters per second. Part II is for Zorb B. So again, we've got its speed of 1.5 and its mass of 60. So it's going to be 90 kilogram meters per second. It is going in the opposite direction, so we can put a minus sign by our velocity and a minus sign by our answers just to show that they're in different directions. Part III is the total momentum, so I'm going to state that this is my positive direction. So I'm going to start with my 150 kilogram meters per second from the first one, take away the 90 for our second one, because they're going in different directions, and that means overall I have 60 kilogram meters per second, and it's going towards the right hand side of the page. Question 4b is after the collisions. They've both bounced off each other and are moving in opposite directions, and now we've got to recalculate their momentums. So we'll take our velocity here. So I did say last time this is our positive direction, so we've got minus 0.8 times by the mass, which hasn't changed. So that's going to be minus 60 kilogram meters per second. And for Zorb B, we've got 2 going in our positive direction, that's our velocity, times by its mass, which is unchanged. So that's 120 kilogram meters per second. And then our total momentum, so we'll take the one in our positive direction, we'll take away the one in our negative direction. So we've got 60 kilogram meters per second as our total momentum after. Question 4c is about kinetic energy. So for kinetic energy, we're going to use half times m times v squared. So part I is to calculate it before the collision. So for A, it's going to be half times the mass of A times the velocity squared, which gives you 150 joules. For B, we've got half times 60 times 1.5 squared, which gives 67.5 joules. And I'm going to add those two up. That's going to give me 217.5 joules. So that is our overall kinetic energy before they collide. After our collision, we're just going to redo those sums, but with the new velocities. So A is going to be half times 75 again, times 0.8 squared, which equals 24 joules. B is going to be half times 60 times 2 squared, which is equal to 120 joules. So if we add those together, we're going to end up with 144 joules. So we can see this is an inelastic collision. We've lost some energy. Part D is just summing up the question. So state whether momentum is conserved. So we know that momentum is conserved. So that'll probably be for our first mark there. And we can state that because the momentum before, I'm going to be lazy and switch to doing a P, was 60 kilogram meters per second, and so was the momentum after. Therefore it is conserved. Part II was kinetic energy conserved. So let's state what we know first. So we've got KE before was equal to 217.5 joules. KE after was equal to 144 joules. So we're going to say the kinetic energy was not conserved because those are both different numbers. And then for the third part, is it elastic or inelastic? So it is inelastic because our kinetic energy was not conserved. So all that spare energy that we've lost from our system in terms of kinetic energy has become a different form of energy, for example, sound. On to question 5. A collision can be described as elastic or inelastic. Place a tick to show which quantities are conserved, provided there are no external forces acting. So we know that momentum is always conserved, regardless of what kind of collision it is, and that's the same for the total energy. But as the previous question showed, kinetic energy is not always conserved because that was an inelastic collision. It is in an elastic collision. 5b, during a safety test, a car or mass, there's a spelling error there, 1,250 travels at 0.5 meters per second towards the wall. Calculate the momentum. So we're going to do this one times this is going to give us 625 kilogram meters per second. Question 5c, the car has a force sensor attached to the bumper which detects the force exerted on the front of the car. The graph shows the variation of force, that means the force is changing with time during the collision. Use the graph to show the impulse is 625 newtons per second. So in case you've forgotten, impulse is just a fancy word for the change in momentum, but we need to work out the change in momentum. So we do need to have a little bit of knowledge of this equation. Change in momentum divided by time equals force. And we are working out the impulse, which is force times time, it's delta P. So force times time on this graph is going to be the area underneath the graph. So we can't just do one simple sum to work it out because our force is changing. We need to work out the area. So if you remember how to do the area of a triangle, it's half times the base, which is 10, times the height, which is 125, which is 625 kilogram meters per second, or 625 Newton seconds. And our final part is to talk about crumple zones in cars. So state how a crumple zone affects the impact time of a collision. So what it does is it increases the collision time. And how does that affect the force? It decreases the force. And that is because our change in momentum is equal to the force times the time. Our change in momentum during a collision is going to stay constant. But what our crumple zone does is it means that this bit is larger, this increases, and therefore our force must be smaller so that our change in momentum is the same. So it decreases the force on us to protect the passengers if we are involved in a crash.